For more videos like this for discrete one, you can take a look at Sarai Studies, link is in the description box below.
Ignore everything that they give you and go straight to what they want you to prove. Your goal is to always try to write what they want you to prove using an if-then statement. So we're trying to say prove that if something, then something else. So what can we say here? Well, we're told to prove that the sum of two consecutive triangular numbers, so the sum of two numbers that are triangular and next to each other is a perfect square. And they give us these two numbers. One of them is tk and another one is tk minus 1. So in other words, we can say if I add two consecutive triangular numbers, so this here can be my P, then the sum is a perfect square. So this here can be my Q. So because we managed to write this in the form of P implies Q, we can try a direct proof, which is used to prove implications because it allows us to say, hey, let's assume that P is true and then try to show that Q is true using axioms, theorems we've already proven, or definitions. In this case, the definitions are given to us. So the proof that we're going to try is a direct proof. But with any proof, no matter what you're doing, you always have to identify the domain that you're working with. So for the domain, use your definitions or the context of the problem. The definitions say that the numbers that we're working with are positive integers, and the perfect squares are hoping to get are also positive integers. So we're working in the set of all integers, but they're not just integers, they're positive integers. Remember that the set of all integers is equal to negative integers, 0, and positive integers. But we're only dealing with positive, so we're going from here all the way to infinity. So we want to specify, we want to say, hey, we're not just working with the set of all integers, we're working with the positive ones only. So we just add a plus sign. Now we're ready to start our proof. So with a direct proof, we assume that P is true. What is P? P is I add two consecutive triangular numbers. So if I'm assuming that I am indeed adding two numbers that are triangular and are next to each other, then what does that imply mathematically? What's the expression for that? Well, they actually give it to us. These are the two triangular numbers that we're adding. But if they didn't give this to us, how would you find out? Well, we're adding, so this implies that we're adding what? Triangular numbers. How many? Two. So we're adding two triangular numbers. How do we denote triangular numbers? Well, a triangular number is denoted as t sub k. In other words, a triangular number at some integer k. So one triangular number could be a triangular number at k, and another triangular number could be a triangular number at another k. Call it k2. So what I'm saying is in the list of triangular numbers that we have, I'm picking one triangular number right here, and this one could be any other one. It could just be another triangular number. But the problem is we're trying to prove that when I add triangular numbers, they have to be right next to each other. So not this one, but this one. So triangular numbers that are right next to each other. So how do we fix this so that this says that the triangular numbers have to be consecutive? To get a better idea of what I'm talking about, let's put some numbers to these words and actually look at the list of triangular numbers. So remember that the domain is positive integers. That does not include 0. It starts at 1. So our first k that we can plug in is 1. So we can find a triangular number at k is equal to 1. So if we do that, we get 2 times 1 is 2 over 2, that is 1. So our first triangular number is 1. So that's at k is equal to 1. So let's continue at k is equal to 2. So let's find our triangular number at k is equal to 2. So wherever we see k, we plug in 2. So 2 plus 1 is 3 times 2 is 6 divided by 2 is 3. So our second one is 3. At k is equal to 3. Triangular number at k is equal to 3. Plug in 3 wherever you see k. So 3 plus 1, that's 4, times 3, that's 12, divided by 2, that's 6. At k is equal to 4. So the triangular number at k is equal to 4. Plug in 4 wherever you see k. 4 plus 1, that's 5, times 4, that's 20, divided by 2, that's 10. And you can continue for the k's up until infinity. But the idea is, so far, we had that this could be tk and then plus tk. 2. So what this is saying is that I can pick any triangular number, let's say it's this one right here, 6, and I can add any other triangular number because we're saying, hey, I'm adding a triangular number at some other k. So that other k could be k is equal to 1 for all you know, so that means we're adding 6 and 1. But the problem is that these are not right next to each other. We're not trying to prove that if I add two triangular numbers, the sum is going to be a perfect square. I'm trying to prove that if I add two triangular numbers that are next to each other, the sum is a perfect square. So if I pick 6, the only other options that I have for what I need to add are the ones that are right next to 6, consecutive to 6, so either the one before it or the one after it. So we know that in this particular example, it's 3 or 10 that can go here. So how can we describe these? Well, the idea is that you get a triangular number at some k. In this case, k was equal to 3. And if you want to get the triangular number right before this one, then all you have to do is subtract 1 from k, because then k will be 2. So you'll be finding your triangular number at k is equal to 2, which will will give you 3, which will be the one right before it. And if you want to get the triangular number right after, we'll just add 1 to k. So it goes from k being 3 to 4. So you're going to find your triangular number at k is equal to 4, which gives you 10, the one right after it. So generally, whatever triangular number you have, you found it at some k. To get the triangular number right before it, you do -1. To get to the triangular number right after it, you do +1. So we can generally describe the triangular number right before a triangular number at some k by taking that triangular number at some k and just subtracting 1 to the k. And we can describe the one right after it by taking the triangular number and adding 1 to the k. So whenever you have t sub k, your only two other options, because they have to be consecutive, are the one right before or the one right after. So you can either add t sub k -1 or t sub k +1. This combo or this combo. In this case, they chose to pick the one right before it, so tk -1. But you could also do this one, and the proof will work as well. So we don't just say, oh, some triangular number at some random k. No, we want to specify that we have to add a triangular number at a k that is right before or after, because these are the only two consecutive options. So that's what they give us right over here. And you can switch the order, it doesn't matter. So when it is true that I'm adding two consecutive triangular numbers, this implies mathematically that we're adding two consecutive triangular numbers, where this triangular number and this triangular number are positive integers because of the definition that says the triangular numbers are positive integers. Now what is this? This is our sum. And remember that we are at P and we're trying to show Q. We're trying to say something about the sum. So we're trying to say something about this. We're trying to say that it's a perfect square. So you would go to the definition of a perfect square. It says that a number that is a perfect square has an integer k that if you square it, it's going to give you that number. In other words, if I want to say that the sum is a perfect square, I have to get it to look like something squared. So right now, let's use what we have. We have two triangular numbers. We know that if we have a triangular number, then it's equal to this stuff right over here. So using the definition of a triangular number, you can say that this triangular number is going to be equal to this, k times quantity of k plus 1 over 2. And if you have this triangular number, so it's tk minus 1. So wherever you see a k, you're going to replace it with a k minus 1. So that's why over here, you're going to see k minus 1, then the plus 1 all over 2. Now with some algebra, we can simplify this. If you distribute the k, this becomes k squared and then plus k all over 2. And then here we have a minus 1 and a plus 1, so these go away. So you're just going to be left with this times k all over 2 right over here. So here you can drop this down for now. And then here we can distribute the k. So this is going to be k squared minus k and then all over 2. Now you can add your fractions because they have the same denominator. So the denominator is going to be 2, and then you can just drop down all the numerators. Now this is a negative k, positive k. These cancel out, and you're left with 1, 2k squares. So you're literally left with 2k squares and then all over 2. Now these 2's cancel out, so you're left with that the sum here is equal to just k squared. So we got our sum to be equal to something squared, which is really close to the definition of a perfect square. But the problem is the definition of a perfect square requires n to be a positive integer. In this case, is our sum a positive integer? Can we say that at the end of the day it's just going to be some number, some integer n? Yes, because at the end of the day, when you add two integers, you're just going to get another integer. We can call it n. That is what we call the closure property of integers under addition or under sum. If it was subtraction, it would be under difference. If it was multiplication, it would be under multiplication or under product. But it only works for addition, subtraction, and multiplication. So we can say that this implies that this at the end of the day is going to be some number, some integer n. At the end of the day, this n is equal to k squared. Now, if you just say this, they might be like, okay, where did you take n from? Like, where is this n coming from? Did you just invent it? So we want to specify what n is. N is equal to, and then what it was equal to, tk minus 1 plus tk. And then specify that n is also an integer. Because of the closure property, you add two integers, you get an integer, so it is an integer. Now what's interesting is that we have some number equal to k squared. And when we have a number that is equal to k squared, this definition says, well, if that's true, this double implication says if this side of the implication is true, and that must mean that this side is also true, so that same number is a perfect square. So this number is a perfect square. So by the definition of a perfect square, this one right here, n is a perfect square. And remember that n is equal to our sum. And we managed to say something about our sum, that our sum is at the end of the day a perfect square. So we managed to go from assuming that p is true to showing that q is true. From p all the way to q. So we say therefore, that's what this symbol means, and then we copy and paste what we wanted to prove, which is this sentence right here. The sum of two consecutive triangular numbers is a perfect square, and we're done with our little proof. And that's it for this video. I'll see you in the next.